Hello everyone, we are now on Module 2 for Foundation Engineering. We are on Ultimate Bearing Capacity of Shallow Foundations, Special Cases. But before we proceed with our concept and principles, let us try to identify our learning outcomes for this chapter. So, at the end of this module, the students are expected to explain that soil may have rigid layer, a shallow depth, or the soil may be layered and have different shear strength parameters. Explain concept and principles for the design of foundation on or near slope. Compute the ultimate bearing capacity for shallow foundations for rigid layer and for foundations on or near slope. Design a foundation subjected to uplift load. So basically for ultimate bearing capacity for shallow foundation special cases, this is different from the considerations that we have encountered or studied in the previous chapter. On the previous chapter, the ultimate bearing capacity problems that was described assumes that the soil supporting the foundation is homogeneous. The soil supporting the foundation extends to a great depth below the bottom of the foundation, and the ground surface is horizontal. So those were the assumptions on the previous discussion on the ultimate bearing capacity for shallow foundation that we have discussed before. It is assuming that the soil that supports the foundation is homogeneous and the ground surface is horizontal. However, that is not true in all cases. There will be possible that you will be encountering a rigid layer at shallow depth, or the soil may be layered and have different shear strength parameters, which is true. In some cases, it may be necessary to construct foundations or near the slope, or it may be required to design a foundation subjected to uplifting load. So these problems, this chapter discusses bearing capacity problems relating to these special cases. So we have to take note that this is different. The consideration on this chapter is different from the previous chapter because the previous chapter, there was an assumption that the ground surface is horizontal and the soil that supports the foundation is homogeneous, but it's not true in all cases because there will be a time that we will be encountering a rigid layer at shallow depth, and the soil can be layered and the soil may be layered and it will have different shear strength parameters, and of course there will be a time that you will be encountering to construct a foundation on the slope or near the slope. So those are the considerations on this chapter. So basically, there will be different formulas that you will be studying and you will be considering, which is dependent on the conditions of the soil wherein you're going to construct your foundation. So we have here foundation supported by a soil with a rigid base, a shallow foundation. So meaning to say, you have a foundation being supported with a soil having a rigid base at a shallow depth. So basically for this, if you're going to neglect the depth factor for vertical loading, so this is an illustration for a shallow, rough, continuous foundation that is supported by a soil that extends to a great depth. So we have here the failure zone for our foundation. And if you're going to neglect the depth factor for vertical loading, the equation that we will be using for this is ultimate bearing capacity Q sub U is equal to C squared N sub C plus Q N sub Q plus 1/2 gamma B N sub gamma. Of course, we know how to compute or how to identify our N sub C, N sub Q, and N sub gamma. Those are bearing capacity factors, and it was identified already in our previous discussion. There was a tabulation, or you can have a formula to get the value for these bearing capacity factors. If the rigid rough base is located at a depth wherein our this D is greater than our H below the bottom of the foundation, full development of the failure surface in soil will be restricted. In such case, the soil failure zone and the development of slip lines at ultimate load will be as showing our figure. So this one is this is a figure showing the failure surface under a rough continuous foundation with a rigid rough base located at shallow depth, meaning to say you have constructed a foundation at a shallow depth. You have a foundation at a shallow depth, and this is the formation of the failure surface. This is the formation. This one is the formation of the failure surface under a rough continuous foundation. So basically for this, according to Mandel and Salincon, it was in 1972, they determined that the bearing capacity factors applicable to this case by numerical integration using the theory of plasticity. So according to the theory, you can obtain that the ultimate bearing capacity for rough continuous foundation with a rigid rough base located at a shallow depth, so can be given with this formula, with this relationship. So ultimate bearing capacity is equal to n sub prime, n sub c asterisk plus q, n sub q asterisk plus 1/2 gamma, b n sub gamma asterisk. And of course, our these are with the asterisk, those are the modified bearing capacity factors. And of course, we know that B is the width of the foundation and gamma is the unit weight of the soil. So we have to take note that when D is greater than H, our n sub gamma, n sub C asterisk is equal to n sub C, meaning to say our n sub Q asterisk is equal to n sub Q and n sub gamma asterisk is equal to n sub gamma. So meaning to say that the modified bearing capacity factors would be equal to the bearing capacity factors, the original value for the bearing capacity factor if our H is greater than D. So this is our H, and this is the value for the D is the distance from the base of the foundation towards our failure surface of our within the shallow depth foundation. So the variations of n sub C asterisk, n sub Q asterisk, and n sub gamma asterisk with the ratio of your H all over B and the soil friction angle phi are given in our figure respectively. So we have here the value for our n sub C asterisk, n sub Q asterisk, and so that we can have the value for the modified bearing capacity factors. What is important here using this chart is, using this figure, is to know the value for our angle of friction. As long as you know the value of the angle of friction, you know the ratio between H all over B and D all over B, you can simply solve or identify the value for our n sub C asterisk and n sub Q asterisk. Those are our modified bearing capacity factors. This was introduced by Mandel and Salincon. So neglecting the depth factors, the ultimate bearing capacity of rough, circular, and rectangular foundations on a sand layer with a rough, rigid base located at a shallow depth can be given with this formula. So we have here the ultimate bearing capacity of rough, circular, and rectangular foundation on a sand layer wherein it is cohesionless, so meaning to say our C is equal to 0. And of course, it is with a rough base, rigid base located at a shallow depth. So the formula is this one. So you have now reduced the ultimate bearing capacity formula for the rough, circular, and rectangular foundation. So of course, the presence of F sub QS asterisk and F of gamma S asterisk, those are modified shape factors. So the shape factors are a function of our H and B and angle of friction. So for that, the value, you can solve that modified shape factors using this equation. So what is important, you have to know the value for M1 and M2 and the value for our B and our L. So the variation, of course, we know that B is the width of the foundation, L is the length of the foundation. And we have to take note that the variations of M sub 1 and M sub 2 with H all over B and angle of friction, so can be shown on this figure. So we have here the value for our, this is the value for our M sub 1 and M sub 2, so that you can have the value for M1 and M2. You simply have to know the angle of friction and the ratio between H all over B. Once you have the value for angle of friction and the ratio between H all over B, you can have, or you can identify M1 and M sub 2, which you're going to substitute to our equation so that we can solve for the modified shape factors. For saturated clay, under the undrained condition, our phi is equal to 0. So meaning to say, the formula that you're going to use for the ultimate bearing capacity is this one. Ultimate bearing capacity is equal to undrained shear strength N sub C asterisk plus Q. So we have here a table, a tabulation with the variations of the values of N sub C asterisk for continuous and square foundation. This is on a clay type soil because phi is equal to 0. So we have to know the ratio between B all over H, and you can have now the value for N sub C asterisk, dependent if that is a square or a continuous foundation. This was introduced by Weismann's analysis and Mandel and Salenkon's analysis on 1940 and 1972 respectively. So according to Mandel and Salenkon, they performed the calculation for to evaluate the N sub C asterisk for continuous foundation. So Weismann also gave the following relationship for obtaining the ultimate bearing capacity of a square foundation. So for this one, this was introduced by Weismann. According to his theory, this is the equation to solve for the ultimate bearing capacity for a square foundation. So it can be reduced to in this form. So this is now the formula for the ultimate bearing capacity for square foundation according to Weismann. Based on his theory, this is the equation to be used to solve for the ultimate bearing capacity of square foundation. So this is a sample problem which states that a square foundation measuring 2.5 by 2.5 feet is constructed on a layer of sand. We are given with the depth of embedment 2 feet, gamma is 110 pounds per cubic feet, angle of friction is 35 degrees, and C prime is equal to 0. A rock layer is located at a depth of 1.5 feet below the bottom of the foundation. Using a factor of safety 4, you're going to determine the allowable load of the foundation can carry. So you're going to make use of this equation. And of course, Q, the effective surcharge, is 220. So based on the figure, N sub Q prime is approximately 90 and N sub gamma prime is 50. So solve for the shape factors using the formula. So you have to identify our M1 and M2. So we identified M1 based on the figures 0.34 and M sub 2 is 0.45, having an angle of friction of 35 degrees and the ratio between H all over B is 0.6. So simply have to substitute on the formula for the shape factors. Then afterwards, using this equation, you can have the ultimate bearing capacity for our square foundation. And since you're solving for the allowable load, you simply have ultimate bearing capacity times this area of our square foundation all over the factor of safety. And basically, we're going to simplify the 26,226 pounds. So that ends for the first concept of the ultimate bearing capacity for shallow foundation special case.